Good morning. My name is Jade. In this lecture, we will talk about the generation of a probabilistic ashfall hazard map of the 2020 Taal eruption. This lecture is a part of the 2020 UPLB CAS Student Faculty Research Conference. Here is what we will expect in this lecture. First, I am required by SFRC to give a short introduction of myself. So, we will do that. But since I am not keen on talking about me, I asked my friend, Her Royal Highness, to give the short introduction. She will join us in a bit. Next, we will talk about a couple of terms that I believe may not be common to most of us, but are common parlance in the fields of earth science and volcanology. Then, we will answer one why and four whats. First, of course, is why the generation of a probabilistic hazard map is interesting. Certainly, I am standing on the shoulders of giants, so I will talk a little bit about the works of those who labored ahead of me. Building on those works, I will then talk about what I did, the computational thingy that I did. Because I did do something, I will then describe what happened, which for all practical purposes is the hazard map. Then finally, with all this technological brouhaha, I will mention something about the question, so, what now? For your perusal, here is the lecture in a glance. Alright, so this time, let me now just call my friend, Her Royal Highness, to perform her royal duties. Will you please, my lady?
Certainly, my dear. I'll do it all the time. Hello, hello. Let me introduce my friend Jade. Jade is a dynamic university servant who plays all the time and works sometime. Biologically, he is a first filial XY offspring of baby boomer parentage. His blood chemistry is found to be nicotine-free, drug-free, alcohol-free, yet gluten-incompatible with elevated concentration of C8, H10N4O2, extracted naturally from the world-famous Batang gas Liberica cultivar during deadlines. Socially, he is an outgoing conservative and considered by colleagues as high-tech low-lifer. Artistically, an abstract realist. On the left is his globally recognized avatar, and on the right is his Kandinsky-inspired digital self-portrait. He is spiritually monotheistic, with a philosophical worldview purely guided by the Judeo-Christian beliefs and the Gospel of the Bible. For him, God is the absolute standard of morality. Thus, he is an ideologue of pro-life, free speech, rights to property, common decency, and traditional family values. His scientific worldview is natural and multidisciplinary, realized in various R&D endeavors. His works exploit the beneficial advances in computing science and ICT. He introduces theoretical and practical innovations on them to optimize and augment agricultural, environmental, and natural systems. Ladies and gentlemen, let's hear from Jade with his lecture, Generation of a Probabilistic Volcanic Ashfall Hazard Map of the 2020 Taal Eruption.
Thank you, my lady. I am quite honored. I am truly in debt of your generosity. Again, in this lecture, we will talk about the generation of a probabilistic ashfall hazard map of the 2020 Taal eruption. I will be using the Filipino vernacular in this lecture, so I may be articulating ideas and points in the mixture of English and Filipino languages. First up, some terms to define. Let us define hazard map, and here is a real-world flood hazard map of Metro Manila. My source for this map is the Mines and Geosciences Bureau of the DNR. This kind of map highlights areas in 2D that are affected by or are vulnerable to a particular hazard. Usually, the hazard comes from Mother Nature. Certainly, This kind of maps help us prevent damage to properties and lives. Now, what is a probabilistic hazard map? Well, this is just a hazard map that was created under some probability condition. In this figure are three hazard maps for the probability of accumulating ashfall exceeding 3 kilograms per square meter, given three different eruption scenarios. You may read a lot about on this work in this paper. Now, another terminology is TephraProb. TephraProb is the term used for fragmental material produced by a volcanic eruption regardless of composition, fragment size, or emplacement mechanism. When TephraProb is airborne, you will often hear from volcanologists the term pyroclast. TephraProb are classified according to size. Volcanic ash has a size of less than 2 millimeters in diameter. Volcanic cinders have sizes that range from 2 millimeters to 64 millimeters in diameter, and volcanic bumps are anything above 64 millimeters in diameter. To compare the relative sizes of the TephraProb particle, let us assume that this small blue dot here measures 22 millimeters in diameter. Now, this big ball here has a diameter of 64 millimeters. This means that this bigger ball is 32 times the diameter of the small dot. Now, if we add a horizontal axis for the diameter, then anything to the left of this small blue dot is considered an ash particle. Anything in between the small blue dot and the big blue ball is considered a cinder. And anything bigger than the big blue ball is a bump. Another terminology is the plume. A plume is the technical term used to refer to a column of tephra that was ejected during a volcanic eruption. Here in this figure, there are two types of plume, a strong plume and a weak plume. These terminologies can be verified from this authoritative source. So, why is this interesting? Well, during the Sunday afternoon of 12 January 2020, Taal Volcano erupted. It ejected gases, ash, and lava. It dropped a layer of unusually wet, heavy ash. Initial estimates pegged a total of 577 million pesos damage to crops and livestock. The eruption also caused destruction of 30% of Taal Lake's aquaculture structures. It was reported by news media that ashfall reached as far north as Bulacan. Now, here is an image of Taal taken by a satellite on 6 December 2019. Here now is the image of Taal taken by the same satellite on 11 March 2020, one day before the COVID-19 ECQ was to take effect. Notice the difference of the surface cover days before and days after the eruption. The color indicates the material covering the terrain. On the left is green, which is practically we can infer as vegetation, while on the right is gray, which we can infer as ashfall or tephra. Here is the plume taken by a photographer right when a lightning strikes. Here is a picture of a city street covered with ashfall. You can notice that the visibility is poor. Here is a photo on rural roadways with motorcycles. And here is a photo of a community helping to remove the tephra deposits in front of their houses on the road. Now, sometime after the eruption, PHIVOLCS published a hazard map for Taal's ballistic projectiles. These ballistic projectiles are the volcanic cinders and volcanic bumps. So, what was done by others. Takeo Suzuki, in his seminal paper, described the modeling of tephra dispersion using known laws in physics. And these laws in physics and this modeling is described in this paper. Now, whatever substance it is, a general model used in the atmospheric transport model, or ATM, is given. ATMs deal with the transport of particles in the atmosphere. Here is the reference for that statement. These substances may be natural, such as dust, oceanic salt, volcanic ash, and maybe natural aerosols. Substances may also be biogenic, meaning coming from the flora and fauna, such as those from burning biomass. Yung kapag nagsunog ka ng ipa during rice harvest week, for example. Another source is, of course, the planet's biggest pollutant, humans, or anthropogenic. Now, ATMs involve three different components regardless of the nature of the transported substance. First is an emission or source model, which defines the emission or production of the substance both in time and space. Second is an atmospheric model, or what we call the meteorological model or numerical weather prediction model, or NWPM, which describes the state and evolution of the atmosphere in which the emissions are introduced. And third, the transport model, which describes the transport and removal mechanisms acting upon the substance. The transport model can follow either an Eulerian or a Lagrangian approach. Eulerian models solve for variables at fixed locations or grid points. Lagrangian models, on the other hand, calculate the trajectories of an ensemble of particles and compute mass concentration by averaging over fixed background cells. Here is the reference for all these statements that I have just mentioned. Next up is what we call a tephra transport and dispersal model, or TTDM. TTDMs aimed at simulating atmospheric tephra transport and or the resulting ground deposit. TTDMs are used for multiple purposes, including, number one, short-term operational forecast of tephra fallout and ash clouds. This work is an example of that type of use. Second, reconstruction of past eruptive events to constrain key eruption parameters by solving what we call an inverse problem. Actually, this is the dual of the problem. Now, this work is an example of solving the inverse of the problem. Third, generation of probabilistic maps for hazard and risk assessment, adoption of mitigation measures, and supporting territorial planning policies. This work is just but one example among the many. Fourth, better understanding of physical phenomena, and this work is a good example of that. And last but not the least is simulation of recent eruptions, normally for model evaluation purposes. TTDMs have different variants, and one of those is the Gaussian version. If topography is assumed flat and the atmosphere is discretized as a series of vertical layers, the Gaussian function can be assumed to spread and settle, while its center of mass translates or moves under the effect of wind and settling velocity. This allows lower computational costs in terms both of space and time. What I mean is memory space and processor time. Example of such Gaussian TTDM is tephra, which was presented in this paper, initially presented in this paper. Now, another technique for modeling is TephraProb, which is a combination of the use of tephra and some ideas in statistics. TephraProb was initially discussed in this paper, while its utility was discussed in this sequel paper. There are a lot more work by others to discuss, but my time is limited. So knowing all this and more, what did I do? First, because of the memory space and processor time consideration, I chose the Gaussian TTDM in TephraProb. Next, I collected wind dataset from the US National Oceanic and Atmospheric Administration. The reason for this is that the Ambolong Pag-asa Synaptic Station is not enough. It's just 1 point. So I need a wind dataset for all the points in the space, vertical and horizontal space. Now, the wind profile from this site is a 4 times daily reanalysis of the wind speed and direction for a given elevation starting at mean sea level. The database contains datasets starting January 1979. However, since this preliminary work that I'm just doing is just a, preliminary, I've limited the wind profile into just the recent 10 years. This is from January 2010 to December 2019. I could not include the 2020 dataset because they are not yet available. I did not use, however, all wind profiles. I only used the daily wind profiles from January 6 to January 18. This is because I'm just simulating the January 12 volcanic eruption by Taal. Now, from this reduced dataset, I manually remove the days when the location was under at least a tropical depression. Now, the reason is that tropical storms and other bad weather alter the wind profile of a certain location. For example, shown here is the wind direction brought about by the recent typhoon Ulysses. So therefore, this might affect the simulation if we will include, for example, days when the area is under at least a tropical depression. Now here's the location of Taal Volcano in the map. Here is the wind profile, just 0.1 kilometer or 100 meters above sea level of the crater. Notice that the crater is some about 300 meters above sea level. Here is the probabilistic wind profile at 1 kilometer above sea level on Taal's crater. Here is the wind profile at 5.1 kilometer above sea level. Here is at 11 kilometers above sea level, and here is more at 15.3 kilometers above sea level, and more at 20.6 kilometers above sea level. Actually, there are more wind profiles in between these 5 elevations, but I'm only presenting these elevations for presentation time purposes. I used the plume height from the Global Volcanism Program database. Here is the website of the Global Volcanism Program showing its entry for Taal Volcano. Based on the Global Volcanism Program, the cumulative number of eruptions over the years is shown. Different colors of the dots mean that the eruption is of different volcanic explosive index, or VEI. Here is the table of the corresponding meaning for VEI1 to VEI8. I will not discuss any more on this, but Taal might be VEI3, which according to PHIVOLC's public notices is Vulcanian and subclinian, which has a plume height of 3 kilometers to 15 kilometers. So I've considered the Taal eruption of 2020 as volcanic explosive index 3. So what happened after I run the program? Here is now the resulting probabilistic hazard map. The map shows an isomass of tephra deposit on a certain area. The lines are lines of equal masses within that area, or within that enclosure. Notice that areas within the crater and the island received a staggering 100 kilograms per square meter of tephra deposit. This is with the conditional probability that the eruption is classified as BEI3 and that the eruption will occur with 50% probability. And you can actually read through the probabilistic hazard map and see if actually it verifies how much tephra deposit you accumulated in your area. Alright, so what now? Well, this is just an initial result of a preliminary investigation, which I started sometime after the Taal eruption and before the COVID-19 ECQ lockdown. I will be conducting more runs and present more initial results to PHIVOX. Maybe in a collaboration with an expert, we may be able to validate the model with their data, specifically the plume height and the corresponding ashfall accumulation per square meter. Actually, I can say that nobody dared measure and record the amount of ashfall accumulated per square area on a particular location. I don't know about UPLB. If we did measure how much ashfall we accumulated, we probably just, swept them away with the PPMSO. We can create more hazard maps that will cater to the agricultural sector, particularly in the area of crop insurance. Similarly, we can create maps for the purposes of assessing the structural strength in built-up areas, specifically the roofing when the heavy ash settles on top. Now, in collaboration with computer science and IT, we may be able to develop an online tool for generating hazard maps for any eruption event at any day of the year. And we can use the same computational technique and procedure for a tool to generate maps for other active volcanoes in the Philippines, specifically Mayon volcano and probably Mount Canlaon and anywhere in the world actually. I am welcoming any faculty or student collaborators so we can achieve these things. This ends my lecture, and next is online audience participation. But before we do that, let me just thank the guy who diligently answered all my emails regarding running TephraProb. Thank you for listening. Good morning.